Is anyone still having issues with mastering at all, or everything's been sorted? Okay, good. Oh, you have a question? Oh, or you have issues? What's wrong? You can't register? Oh. Did you email me this?
Yeah.
Okay. Yeah, I remember. I am not familiar with that problem. I don't know how to solve it. You might have to talk to Pearson directly, or if
I think you just have to register again because it gives me that same issue as well. But if that's registered again.
Alrighty, well, it's now the official start time for class. Today's going to be, the first couple of lectures are going to be a lot of me talking, unfortunately. So, but we'll get to some more interactive stuff after about middle of chapter 3. But, so it's a chemistry class. Probably talk about what chemistry is. Chemistry is the study of matter and its changes. So when you study matter, you're doing chemistry. We'll talk about some other sciences in a second. Before we get there, though, let me tell you about a very dangerous chemical, DHMOs. Anyone ever heard of DHMO? No one. So it is a very powerful greenhouse gas. It's set to cause about 80% of global warming. Much, much more powerful than CO2. It's used in nuclear power plants, especially like Fukushima. We find it in cancer cells, used in animal research. And we have a huge investment of this in warfare for its use, DHMO's use in warfare. So, as I've mentioned before, this is kind of a joke. Does anybody know what DHMO is? No one heard it before. Wow.
Hydrogen monoxide.
Dihydrogen monoxide. It's water. Everything I said here is true. Water is the primary greenhouse gas for the Earth. So the Earth has a very strong greenhouse effect. And if it wasn't for water, the Earth would be much cooler. Has anyone ever been to a desert before? A desert? What's it like during the daytime?
Hot.
What's it like during the night? Yeah. And what do we know about deserts? They have less water. What the quality of life there is a different story. We use water in nuclear power plants found in all cells, right? There's a 100% correlation for mortality for those who consume dihydrogen monoxide, right? So you need to give animals water. And has anyone ever heard of the Navy before? Right, so everything I said here is true, but you can really skew the facts. Or not, I guess, well, this is the facts, but you can skew your perception if you don't understand what the basis of it. There's a huge website called Ban DHMO. I could look that up. Let's see here. Ban DHMO. So, Coalition to Ban Dihydrogen Monoxide. But, anyways. So, but we jump around quite a bit in the first couple of chapters. So I know you as a student, you're like, oh geez, a new topic, my favorite thing. So, but that's just kind of the way it is though, for the beginning. We'll get into much more coherent, focused learning after about chapter 4 and 5. 4 is pretty coherent, 5 jumps around a little bit. After that, it's pretty consistent. Okay, so this is a science class. So what is a science? You've ever heard people say, this is a science. What does that mean when you say it's a science? It means that you're using a systematic approach. And science specifically, it's a systematic approach to solving problems. I want to approach this scientifically. What do you mean? I'm doing systematically. That's what you mean by that. And we have here the different types of sciences. There's more, but these are kind of known as the big 3: biology, physics, and chemistry. So biology is the study of life. Okay, so physics is the study of the physical world. To me, physics is how long the vector is and where it points. So like my center of mass here is pushing down towards the center of the earth, and the floor is pushing back with the same force. So that's why I'm not moving. right? So that's kind of what physics is in my mind. I'm describing it. And then we have chemistry, which is this class. Chemistry is the study of matter. A couple types of chemistry: synthetic chemistry, physical chemistry, and biological chemistry. That's kind of what we organize ourselves in. I myself am a physical chemist. Most chemists are synthetic chemists. Like my father, he's a synthetic chemist. Those are the people that actually make stuff. Like you think of like Heisenberg in Breaking Bad, he's a synthetic chemist. I'm more like, I know this show's canceled now, but The Big Bang Theory, I'm more like Leonard. So maybe not necessarily in personality, I hope, but maybe more like Sheldon, who knows. But I mean like vacuum chambers and tubes and lasers. That's the kind of stuff that I've worked with. And okay, so science uses a scientific method, and here is the scientific method, at least an image of it. So idea is we start off with observations, and this is really what brings us to contemporary science. We run science off of observations and experiments. We don't run it off of philosophy. So observations, so get data, and if you gather enough data, you can form a scientific law. So scientific law is a summary of data. So it can be, a scientific law can be a concept. I don't think I'm being heavy. Here we go. Like the law of gravity. What goes up must come down. What goes up must come down. I can do that. The law of gravity, spend all day verifying it, right? That'd be a very boring class day. Very boring day. You can have laws be equations. So ideal gas law, that's one we're going to talk about in chapter 6. PV equals nRT. So force is mass times acceleration. That's Newton's second law. So you can have it be equations. You can have it be statements. Law of conservation of matter. Matter is not created or destroyed. So these types of things. Okay, so observations. Now here, this is what I see more of the scientific method though. Observations to form a hypothesis, then experiments confirm or deny a hypothesis, and if enough experiments confirm a hypothesis, then a theory can be formed. A theory is an idea, it's a proven fact. So let me cover a real simple one. Let's say my car does not start. I want to get up, come to class, my car doesn't start. I'm going to say, okay, my car doesn't start. I'm going to hypothesize that I'm out of gasoline. So I'm going to put gasoline in the car still doesn't start. Like, all right, maybe my battery's dead. So I get someone to jump start my car starts, and like, okay, I've now verified that my battery was dead, and now that has become a theory. The theory of Mike's car not starting is because of a dead battery. But that's a real simple theory, though. Theories are much bigger. Things like germ theory. Germ theory is that diseases are caused by pathogens and not by evil spirits and bad air. So we used to believe that. We really used to believe that. And so theories can also be wrong. So theories do not necessarily describe everything. There are illnesses that are not described by pathogens. So we have mental illnesses. We have certain cancers, most cancers. Some people can argue that some cancers are from diseases, but you can get cancer and not have a pathogen. You can have occupational illnesses like contact dermatitis, that's forever inflamed skin. That's a disease. So those are not caused by pathogens. So it doesn't mean that one theory can describe absolutely everything. So, and we're aware of the holes in our theories. I mean, we know that there's a problem right now with our physics. We have two competing theories. We have quantum mechanics and we have general relativity. And we can't start off with protons, neutrons, and electrons and come up with the gravity of the sun, for instance. We can't build that up. We don't have a grand unifying theory yet. Okay. So, and also theories can be tweaked. We can learn more and more things. I mean, germ theory obviously has gotten a lot better. Atomic theory has gotten better. Okay, let me go back. With observations, so I mentioned observations. Observations can be either quantitative or qualitative. Quantitative is a number-based. There are 7 students in this side of the classroom. So that would be stage left. So stage left here, there are 7 students sitting down. This is a small classroom. That's an idea. That's a qualitative idea. So when there's a number, it becomes quantitative. When it's an idea, it's qualitative. The sky is blue. That's a qualitative idea. The sky's color appears to be about peaks at 500 nanometers of wavelength. Oh, that'd be green. 550 nanometers. That would be a quantitative. Okay, then hypothesis, as I mentioned before, educated guess, experiments test the hypothesis, and theory is a proven fact. And what's also scary is your theory can be wrong, but can still predict the right things. We're going to cover theories that are incorrect in this class. Like basically all of bonding that we're going to cover is actually incorrect, although we still use it. It's a very useful theory, but we still use it. So I mean, one of the strongest theories is that there's only 4 elements: earth, wind, fire, water. That's a very powerful theory. It describes almost everything. I mean, of course, it's incorrect. We have 118 elements, not 4, but at least as far as we can tell. But you could predict many things using the theory of earth, wind, fire, water. Okay, so theories can be and often are wrong. Laws can be broken. We can break the law of gravity. We can break the law of conservation of matter, law of conservation of energy. We know these things. Also, science is tentative. So science is very tentative, and it's also experimentally based, not off of models or simulations. This is a big change that happened around 1850. So I'll give you an example of something. So maybe you've heard of Platonic love before from Plato. So Plato is a philosopher and a Greek philosopher, and he came up with the idea of perfect love. Perfect love was between 2 men, and it was relationship based. That was like friendship. That was the perfect type of love. Of course, colloquially now we see platonic love can be between males and females, and we think that women have the ability to love alongside men. But this is ancient Greek philosophy, right? So, and the whole word platonic, when you say something platonic, Plato believed that there was this form of something in heaven, and then everything was related to it. Like there was a perfect water bottle, and it was in heaven. And then we relate this water bottle, that perfect water bottle in heaven. This one has a dent in it, right? So this is obviously not the perfect water bottle, but it's close. So Plato would argue things like, well, this is the way things should be. And that's how a lot of science was. Like illnesses, they thought illnesses were from the 4 humors as well. That's another incorrect theory, that there were 4 humors. It was like blood, phlegm, green bile, and yellow bile. And if you were sick, if they were not in balance, and usually they bled people. Like you have a cold, you have a runny nose, you have too much phlegm, let's get rid of your blood. So they bleed you. But of course, that's not a very good way to do things. Or it'll stick some leeches on you if you don't want to bleed you. Okay, so science is tentative, and it's based off experiments. And correlation does not equal causality. So this is a big mistake many people make. There are several examples of these. One, you ever read the book Freakonomics? I think that book's fun. But one of them was that they found that there was a very good correlation between polio outbreaks and ice cream sales. They correlated very, very well. So they were telling parents, like, don't buy your kids ice cream, they might get polio. And the reason why they correlate is because when it's summertime, people intermix. And when it's wintertime, you don't go to it's here in Hawaii, the winter's nice, but like the East Coast, it's snowy. So wintertime comes along, you're not going to go to the park, you're not going to go to the swimming pool. But in the summertime, you will, and when people intermix, then diseases spread. So that's the reason why. There was a common third factor. But limiting ice cream sales is not going to stop polio. And also, science is very powerful. It puts people away in prison. So when I was prepping for the semester, I was watching some stuff on Netflix. They're talking about the the forensic cases that put people away and were later proven to be wrong. I forget what it's called. But, I mean, science can put people in prison. And also, bad science can severely injure people. There was this science called eugenics. So it's the idea that that human beings have different races and that there is a superior human race. So first of all, there is no such thing as different races of humans. There's only one. You could argue that there was the Homo neanderthals. Neanderthals? Yeah, but and according to 23andMe, apparently I've got a little bit of their blood in me too. So, but for species, we have. So if you can form an offspring from the same member of the species, that offspring, if that offspring is fertile, then you're considered to be the same natural species. So, of course, we still colloquially do this. Say, what race are you? And you're like, well, human. You know, and you're like, no, you could argue that humans have subspecies, but humans don't fit very well for that because we intermix so much. So we don't really truly have subspecies like Amur tigers versus Bengal tigers versus Sumatran tigers. Those are clear subspecies. They have been separated. They have regional adaptations. But with humans, we've mixed so much that we don't really have subspecies anymore. At least we don't fit the mold for it. But eugenics basically was white supremacy. They said that that whites, especially the Nordic, was the most superior race, and then if we had to make sure that whites and non-whites did not mix, because then all the non-whites were going to go extinct because of their inferior genes, and then if we don't pollute that, then we can cause the extinction of the human race. That was the idea. Some people still believe this. But of course, it's complete hogwash. It's terrible, and it's really injured people. We here in the United States, we sterilized about 300,000 Puerto Rican women, so because of eugenics. Yeah, this was back in the 1960s. So, I mean, obviously other countries have done worse things, but we are not completely innocent here in the United States either. And 1967, there was a Supreme Court case, Loving versus Virginia. That was called a miscongenation law. So it's the different genus, different. So the idea, whites were not allowed to marry non-whites, and that was a famous case because the Loving couple was a white male, black female. They got married, and Virginia arrested them. And that case was, in 1967, was overturned. So that was a big deal back then. So it's not like this was a long time away, this type of bad science. Eugenics, more or less, started, although we in the United States had it a little longer. In Germany, if there's any forms that ask for nationality, there's riots. They're very sensitive about this issue. We still do it here in the United States, though. But oh well, here's the eugenics. Okay, so what is bad science? Uses correlation, relies on models, and consensus. Consensus doesn't mean anything. Consensus is important for democracy, not for science. Okay. I know I'm talking a lot. Does anybody have any questions? I know that, and we're going to change topics yet again. So, states of matter. So, solid, liquid, gas. My cell phone is a solid. It has a set shape and a set volume. The shape of it is a rectangular prism shape. So in the set volume, this is, I don't know, 100 milliliters-ish. I'm not sure. And there's two types of solids, crystalline and amorphous. So most everything is amorphous. Very few things are crystalline. So here is a diamond. Diamond is crystalline. And it has the zinc blende structure. The atoms are all organized very regularly in space. Amorphous, irregular pattern. So Iron tends to be about, I know a lot about iron because I studied it in grad school. So iron, its surface tends to be about 90% it's called the 110 surface. But there's other surfaces, but it's not a crystal. It's not a crystal at the surface. It's very randomized. And crystals, we tend to think, they're also more valuable. So my MacBook here and my water bottle. Does anybody know what you're looking at right here? I know it's aluminum, but you know what the surface is? It's sapphire. It's aluminum oxide. That's sapphire. And you can buy sapphire rings too. I got this for like what, $10 for 2-pack at Costco, right? So I mean, this is not very valuable sapphire. What makes the gemstones more valuable because they're crystalline. And although a lot of it is inflated in price, because like when you buy class rings, those are sapphires. Most synthetic gemstones are sapphires. They're easy to grow. So, but the natural ones now, I guess they're the more special ones. We do inflate certain things. At least the diamonds and gemstones are not really worth what they're worth. So okay, so liquid has a undefined shape but a defined volume. So I know this is not transparent, but if you were to look at the water in this, it's about this high. The shape of this is a cylinder right now. Now it's a half cylinder, right? And I can pour it on my desk, and then it would spread out to be really thin like a pancake. And if I was very careful, I could scrape it all up. I know I'd lose some to evaporation. It gets stuck in the cracks. But the idea, though, is that the liquid's volume is the same. So when I go to a recipe, when I have a recipe for something, and it asks me for a half a cup of oil, I'll take my cup holder and I'll pour a half a cup of oil in there, and then I'll pour it in my mixing bowl. Not am I ever like, gee, is the volume of that stuff going to change? No, it's a liquid. The volume stays the same. I know I lose some. It's going to stick to the walls of the measuring cup. But I mean, in my mind, I'm like, okay, this has the same volume. So liquids have a set volume, and gases have neither set shape nor set volume. So like if I took the tire off my car, and please don't try this experiment, at least with my car. What if I took the tire off my car and brought it here, like, what's the shape, what's the volume? Like, well, it's the shape of the tire, volume of the tire. And if I slash a tire and all air goes out, you're like, what's the shape, what's the volume? Like, well, shape of the room, volume of the room. So gases just fill their containers. And gases, these are the most diffuse types of matter. Another question is, what about plasma? Is that the fourth state of matter? Plasma is just an ionized gas. So it's a gas that has electrons ripped off of it. So here are the states of matter. Here's solid, has a very set structure. The atoms, molecules do not move that much. Liquid has, they hang out together, and it's relatively concentrated, but it's not a set structure. And then gases, they just fly off. So let me give you an example. So water, we'll learn later, water is polar. And here's ice. Ice is just water in a structure. And then temperature is average kinetic energy. So what happens is water starts moving, it heats up, it moves. And then if it has enough energy that it breaks the attractive bonds between it, then the water will melt. And now it's liquid water. And if it starts getting faster, then it breaks apart. And because then the forces can't hold it together, breaks apart, becomes water vapor. So boiling point and melting point of matter is a measure of how attracted they are to each other. And a high boiling point means that you have enough energy to rip the structures apart, or between the liquids and or sublimation for solid to gas and so on. But we'll talk about that more later. And okay. But much of this stuff you probably already know, though. You probably know this already in general about the different states of matter. Oh, another thing, sometimes you hear the condensed phases. Solids and liquids are called the condensed phases, and that's the vapor phase. And there is much, generally speaking, there's much more matter in the condensed phases than the vapor phases. So to give you an example, right? Air is a gas, and I can feel it. I'm waving my arms. I can feel the air. It's pretty easy to do, though. I mean, I'm not like struggling. Maybe like this is not hard. What about doing underwater? When you're doing underwater, it's pretty hard to do that. I mean, I enjoy swimming, but it's much harder to do that in water than it is in air. Why is it harder? Because I have to push about 1,000 times as much matter out of the way in water. So more or less, water is about 1,000 times more concentrated in matter than air is. And that illustrates why vapors just don't have as much matter to them. Oh, and we have the windmills. I guess you can't see me. I'm looking at Haleakala. But the windmills, right? You look at them; they're huge. Have you ever seen a hydroelectric plant before? They're tiny. They're not very big at all. Why? Because there's so much more matter in water than there is in air. That's why you need big fan blades on turbines, because of how diffuse air is. Okay. And this stuff should all make sense, but it's a different way of looking at things. But let me talk about how to classify matter. And I like to start with the most general and break it down, and then go back up. So most everything that we see is a mixture. And mixtures can be two types. They can be heterogeneous or homogeneous sometimes, called as homogeneous. So hetero means different, homo means uniform. So heterogeneous is a not uniform mixture, and homogeneous means a uniform mixture. Has anyone ever seen milk from a cow before? Mm-hmm. Like you take milk from a cow. What's it like? Is it uniform? No, it separates, right? You take milk from a cow, first thing that happens, it separates. You have cream on the top, you have milk on the bottom. So that is a heterogeneous mixture. And what about the milk that you buy in the grocery store? Is that a mixture, or is it? Oh, it is a mixture. Is it uniform or is it non-uniform? Uniform. What does it say? It says pasteurized and homogenized. Yes. So milk you buy in the store is a homogeneous mixture. And but it's a mixture. Milk contains many things. It has pure substances. So it has water. It has calcium phosphate. That's the calcium in milk. It has proteins like whey, right? It has other binders in it, like fatty compounds. So, and actually everything I mentioned there is a compound. Whey is a protein, which means it has carbon, hydrogen, oxygen, nitrogen, and sulfur in it. So those are elements. Water, H2O, hydrogen and oxygen elements. Calcium phosphate, calcium, phosphorus, oxygen, all elements. So you can take compounds, which are pure substances, and you can eventually break them into elements. And you get to an element, we have 118 of them that we know of. About 90 or so are naturally occurring. We call naturally occurring here on Earth. It's debatable how many are naturally occurring. But okay, well, let me pretend we have an element. Say I've got a long carbon rod. I can break that rod in half, take that half, break it in half, then break that in half, keep on going. I get to a point where if I break that particle in half, it no longer is carbon. That ultimate particle of an element is an atom. And we'll talk more about atoms next class, a whole week from now, Wednesday. And let me mention, I mentioned the elements. Wrong class. There we go. Here's a pretty periodic table. But here are the elements. We have 118 of them. Here on Earth, we can find naturally up to uranium, and we can find plutonium in small amounts in nature. It's arguable if if we can find it or not. Technetium and promethium here. These are radioactive and unstable. You probably don't find these in nature. We can make them, but you probably don't find them. So typically say these are out, and then so that puts us to 90. But you can argue that there's a little bit of neptunium, a little bit of plutonium in there as well. So it depends on whom you ask. It's debatable how many are naturally occurring. But another thing, notice they all look about the same. I mean, if I showed you, here's neodymium. I mean, it's a silvery. Most of them are metals, and it's a silvery metal. I mean, just looking at this, I would have no idea that's neodymium and not silver or titanium. So most elements look the same, as in they're silvery metals. Even beryllium, this, that's a silvery metal. Other ones, so copper is this reddish color. Gold is a yellow color. Osmium has kind of a bluish tint to it. And so does potassium, has kind of a purpley color to it. Both osmium and potassium, it's from their oxides, though. It's not necessarily the metal itself. Question?
How come the higher ones, the man-made ones, don't have the same numbers? Like if you look at the chart, if you look at like 118 in the lab, they were showing that. So for like all the other ones.
Handsome fellow. Okay. What do you mean? You mean on the periodic table?
Yeah.
Because they're older. This is only recently discovered, and some. Let me see if I have it on my other periodic table. Yeah, see, this one is missing. This one's missing some of them. Just because when this was published, they haven't been discovered. So, okay. Other questions? Oops, wrong. I'm jumping back and forth. Okay, so I mentioned that most everything is a non-uniform mixture. We are non-uniform mixtures, right? We have different tissues, skin, bone, blood, different fatty tissues, right? We're complete mixtures. Pizza is a mixture, right? The top is different than the bottom. So that's what we see. Most everything is like this. But we can do with elements, so let's do it backwards. Elements can form compounds. So you can have just plain old elements, and you can have, in different ratios, they form compounds, like water is 2 parts hydrogen to 1 part oxygen. And we can get different compounds from the same elements. We'll talk about this next class. That's so hydrogen peroxide. It's 1 part oxygen to 1 part water. So that's hydrogen peroxide. But we'll talk more about the law of multiple proportions later. And then from these compounds, we can mix them together to form uniform substances. And we can put other compounds in it that make it non-uniform as well. We can have non-uniform mixtures with just 2 elements. So nickel and iron. If you've ever seen these, I have a ring of this. It's a nickel-iron meteorite. So nickel and iron, they can mix together, and a little bit of nickel can go into a lot of iron, and a lot of iron can go into a little bit of nickel. And you get these 2 phases, and it looks really pretty. And that is a heterogeneous mixture, and it just contains 2 elements. So you can just have 2 elements form mixtures. You have 2 or more elements form homogeneous mixtures. Another word for homogeneous mixture is a solution. So a solution is a homogeneous mixture, however you want to say it. Homogeneous tend to be more British. So homogenized. I can't really do a British accent. So alloys. alloys are solid solution. So 14 karat gold. It's a mixture of copper, silver, and gold. And it's uniform. 3 elements forming a uniform mixture, a solid solution. Okay, and so where are we at? Analogy I like to use. So how many letters in the English alphabet are there? 26. Yeah, not a trick question. You're paying attention though. I appreciate that. Think of the elements like letters. And when we have letters in the English alphabet, when we put them together, think of those words like compounds. And you can even change properties of letters when you bring them together, like the letter T and the letter H. So, right, T and H are going to make a th sound. So we completely change the properties of T and H when we bring them together. Same thing is true for elements. So about a third of people have a nickel allergy. So about a third or so of people cannot touch nickel. Well, they can, but if they if you have like a belly button ring or something like that, sometimes people, it looks really inflamed. They probably have nickel allergies, and then it's white gold. They put nickel in white gold. Many people have nickel allergies, and I ended up getting braces later on in my life. And I had braces when I was a kid, and I had something wrong with my teeth. I had to get braces later. And since I like chemistry, I was talking to my orthodontist. I'm like, what metal are you putting in the braces? He goes, oh, it's nickel titanium. And you're like, oh, really? He's like, well, I don't have a nickel allergy, but wouldn't a lot of people get allergies to that? And he's like, oh, no, nickel titanium is fine. No one ever reacts to that. So titanium has been well known to people tolerate titanium very well. But nickel titanium, it makes it stronger so they can be thinner, and it's cheaper. Nickel's cheaper than titanium. So having that is just like the letter T, letter H. You've completely changed the properties of those two elements, and now people can tolerate it, or everyone can. Everyone can tolerate it. I don't know. There's probably some people that can't tolerate that. But okay, so compounds are like words, like letters to form words, and mixtures are like stories. Okay, so the tea with sugar story and the story of the human body. Let's say instead of 26 letters, let's say we had 118. So that would make things a bit more complicated, right? And the language of chemistry is much more elegant in a way. I don't know, maybe I'm being arrogant there saying elegant. But the truth of the matter is a lot of the elements look about the same. Most of them are metals, and they look about the same, although we use quite a bit of them in electronics. So there are many subtle differences, and we use them differently in electronics. So if you see like with the rare earths, that's going to be one of the big things with the trade war that's going on, because China is where we get our rare earths. They haven't played that card yet. We'll see. How we doing? So we doing all right? So hopefully you've understood this. We start with the most general heterogeneous mixtures. We can break them up to uniform mixtures, and that into a pure substance, compounds and elements, and eventually break the compounds and the elements. And the smallest particle of an element is an atom. And we can go backwards. We can take elements, we can form compounds, and those pure substances, we can mix them together to form uniform mixtures and non-uniform mixtures, and most everything is a non-uniform mixture. So is everyone good with that? Okay. All right. So changing topics yet again. Physical property. So a physical property is something you can observe without a substance change. So you can look at my shirt, and I am wearing a black shirt today. You are observing the color of the shirt by it still hasn't changed. My shirt is also flammable. And if you verify it being flammable by burning the shirt, it is no longer a shirt, right? It is a pile of ash. And so the chemical property deal with composition changes. So physical property you find without a substance change, color, magnetism, boiling point. So phase changes are a physical property. So you can take an ice cube and you can melt it to form liquid water. You can boil it to form water vapor. You can condense it back down to form liquid water, and you can freeze it to form ice. It's still water. It's still H2O water in its solid liquid gas phase. So that is the melting point, boiling point. These are all physical properties. Chemical properties deal with composition changes or lack thereof. So let's say, and we have culturally, we have a practice where we put things around our fingers to remember a promise. So think of something, tie a piece of string around your finger. So that's why we give rings. So what if I turned to my girlfriend at the time, now wife, what if I said, "My darling, I love you. My love for you is as strong as iron. And as because of that, I'm going to give you this iron ring." You know, why is that funny? What do we know about iron? It oxidizes, yeah, it rusts. So my love for you, if you don't care for this ring, it will turn flaky and brown and fall apart, just like me. So that's probably more of an accurate representation. No, we actually give rings based off their chemical properties. What kind of rings do we give? We give gold, silver, platinum, palladium, rhodium, right? We give things that are non-reactive. It's not the value. Those things tend to be valuable, but I mean, there are lots of substances more valuable than gold. Indium is more valuable than gold. And that's, let's see, weapons-grade plutonium is extremely valuable. Mm-hmm. So why wouldn't we give weapons-grade plutonium as rings? Because, well, besides they're poisonous. But I could imagine that would be like some rich person somewhere would do that. No, we've always thought gold was cool. We thought gold was magical because it doesn't rust. And we always thought diamonds were interesting too. Diamonds are interesting because they're always cold. So diamonds have a very high thermal conductivity. And so when you hear rap songs, when they talk about diamonds, what do they call it? Ice. Diamonds are these magic rocks, and they're, a lot of them, the big ones are white. They're these magic rocks that are always cold. Because if you see a diamond, you're like, ooh, and you pick up the diamond, like, oh, that's cold. You put it down. And but the key is if you hold it long enough, it'll equilibrate to your body temperature. But typically speaking, most of the time, the ambient temperature is lower than the body temperature. I mean, of course, you go somewhere like Qatar or something, then it's going to be pretty hot there. The diamond ice trick probably won't work there. But if you're in, like, I don't know, Europe, where it's always cold, right? You're like, ooh, what is this? Like, ooh, it's magic. Ooh, it's ice. So we always thought diamonds were magical. We always thought gold was magical. And we still do to this day, in a way. Because gold doesn't rust and diamonds are always cold. And diamonds, like I said before, are way overpriced. So here's some pictures. So physical change versus chemical change. So here is the sublimation of carbon dioxide dry ice. And I'm assuming that everyone already knows what atomic theory is. I know we jump around. Occasionally I get students that never heard of atomic theory, but I think it's pretty well understood in society. But there's carbon dioxide, two oxygens, one carbon, and in solid form and then get vapor form. And so this is a physical change only, a change of state. Dissolving sugar, there's sucrose, sugar, and dissolved in water. It has not changed the substance. It's now just sugary water. So this is a physical change. And here is the burning of propane. Propane plus oxygen has made carbon dioxide in water. This is a chemical change. The atoms have rearranged. So chemical change, the atoms have rearranged. Oh, and I use a lot of symbols in class. This is the capital Greek symbol delta. So the Greeks have an alphabet, alpha, beta, gamma, delta, so on. So this is the letter delta, and this is the capital. There's upper and lowercase. The uppercase delta means big change. The lowercase delta means incremental change. So if you ever see a symbol that I use, and there's a lot of symbols used in science. This means big change, meaning macroscopic change versus if you've studied calculus, a derivative, that's an incremental change with the delta in the bottom. Okay, so, or it can also mean partial. Little delta can also mean partial. So physical change is a change in state or appearance. Chemical change is a change in composition. Okay, so determine what kind of property, determine whether each change is physical or chemical, and which is demonstrated. So first one here, evaporation of rubbing alcohol. So you put you probably put rubbing alcohol on your arm or something like that, and it evaporates. It feels really cool, like literally cool, like it feels cold. But that evaporation is just a physical change only. There's no chemical change. The burning of lamp oil. So you burn something, as we stated before, that's a chemical change. You're rearranging the atoms. Frequently, you see a physical change accompanying a chemical change, right? So digestion is a chemical change. You eat some broccoli, the broccoli is green, and then it becomes something that's not green, right? Color is a physical property. So there was a chemical change, and then there's a corresponding physical change. The question is this a physical change only, or is this a chemical change that has a corresponding physical change? Bleaching of hair with hydrogen peroxide. So this is a chemical change. Hydrogen peroxide will actually absorb carbon dioxide from the atmosphere, and it'll bleach the hair. Formation of frost on a cold night. So that is deposition of from vapor, water vapor to solid water. That's deposition then of water, of solid water. That is a physical change only. You see this in your freezer as well. So you ever notice that you buy something like peas, and occasionally, like once every 5 years, I'll decide that I want to start eating peas and rice, and I'll buy a big bag of peas at Costco, and 3 months later, like there's frost. I go to get peas, and there's like a big chunk of ice, right? And there's shriveled up peas. What's happening is in the freezer burn is the ice inside of the food sublimes, and then it deposits outside of it. So it's a solid to vapor, then vapor back to solid. That's the freezer burn. Okay. How are we doing so? Anybody have any questions? All right, changing topics yet again. So energy. So the chemistry definition of energy for this class is capacity to do work. So I don't have any children, but I guess I have cats right now. I'm fostering 4 kittens. And they have lots of energy. And what they do with their energy, you can hear them running around. They're running around playing. Sometimes I have them chase, the red dot laser beam. So they have lots of energy. Could they be using that energy to do something productive? Like, I guess so. I guess I could train them to fetch the mail or something like that. I don't know. So they could be doing work, but they're just, they're cats. They're just running around. So energy is the capacity to do work. Physics has a better definition. Physics is the physics definition. The integral, the force, vector dot product with the path length. So if you've heard of a joule before, a joule is a Newton meter. So if you have the force of a Newton, this is way more than a Newton, but if you take the force of a Newton and you extend it over a period of 1 meter, that is a joule. That's the work. So okay, but we have different forms: potential energy, kinetic energy, and electromagnetic energy. Here, some examples. So and what type of energy is chemical energy? The calories in food, that is chemical energy, and it's potential energy. So it's stored energy. I eat the donut, and then that 100 calories from eating the donut, I guess I could go and run a half a mile, in theory. Of course not. I'm going to be binging on Netflix instead, right? So food and chemical energy is stored energy, potential energy. The good old-fashioned physics example is we don't have to store energy chemically. You can do it gravitationally. I'm not going to draw. It's like the book has potential energy now, and then if I drop it, now it's turned into kinetic energy, which is also how our water spigots work for most places. They put water towers up high, they put water tanks up high, and then you turn on your valve for your water, and then the water flows down. That's just water flows by gravitational potential energy, turning to kinetic energy. So, okay, and forces, energy comes from force, the force along the path length. This is outside the book, but I like to teach it. We have 4 fundamental forces, and you see I've listed 5 here. There's 4 fundamental forces. The 4 now are gravity. Gravity is the weakest force. It is, as far as we can tell, it's only positive. And all matter feels a weak attraction. Also, antimatter and matter feel the weak attraction of gravity for each other. Then there's electromagnetic, sometimes called electrostatic. That is basically like charges repel, unlike charges attract. Also, magnetism, if you take physics, there's a lot more stuff with magnetism. Magnetism makes things twist and turn. Chemistry is basically an application of the electrostatic force, electromagnetic force. Nuclear weak, nuclear strong. Spoilers coming up. Atoms are made of things called protons, neutrons, and electrons. Protons and neutrons are found in the nucleus. There's an attraction of them. That is the nuclear strong force. Protons and neutrons are made of smaller particles called quarks. What bind them together is a nuclear weak force. Turns out that these 2 forces, electromagnetic and nuclear weak, are the same force. So that means we only have 3 fundamental forces. Then we have this idea of dark energy, though, and we have no idea what it is. Dark energy, from what we can tell, the universe, space and time started about 14 billion years ago, and the universe has been expanding since then, which is what's strange, though, is that the universe is accelerating. So you'd think that there's an expansion event, there would be like, okay, it's going to expand and go like this. Actually, the universe is kind of going like that. It's speeding up as it's expanding. And we don't know why, so we call it dark energy. So you can argue how many forces we have, but some people say these are the 4 fundamental forces. Some people can say 3, so it's anywhere from 3 to 5. Take your pick. Okay. Are we doing some questions? I know I'm gonna have a sore throat at the end of the day. I'm gonna be talking so much. Hopefully hopefully you guys are doing okay. Don't worry, not every class is gonna be like this. You might feel like this after the first couple of classes. Okay, so next thing to talk about is the metric system. And if this wasn't the United States, this probably wouldn't be a big deal. But we use the imperial system instead of the metric system. And the metric system is an engineered unit. So if you, I have a degree in chemical engineering, and I can tell you using the metric system for calculations is so much easier because all of the conversions are all factors of 10. So it's real easy to do the math. Although colloquially, it makes a lot of sense. It's about 15, 20 feet from here to the wall, instead of saying like, oh, it's like 5 meters or so. No, that's about right. It's like 5 meters to the wall. That's, because there's 12 inches in a foot, and then 3 feet in a yard, and 5,280 feet in a mile, right? So we have these weird numbers. But the metric system, we have a few base units. Here's the base unit. Meter, about this long. Kilogram, second, temperature is Kelvin, amount is mole. Then we have current, ampere, and then luminous intensity, candela. Truth of the matter is we don't use candela anymore. We got rid of candelas. We use watts now instead of for light. We typically talk about it in watts. Use light as energy. But so the nice thing about this is that everyone agrees on time. Can you imagine how the world would be if we didn't agree on time? Like we all agree, second, minute, hour, day, year. There's not anyone who says, you know what, we're not going to use a second, we're going to use something else. So we all agree on time, and we also have the Babylonians to thank for that, from the 60. The 60, they like the 60 base things. So 60 seconds in a minute, 60 minutes in an hour. And same thing with degrees. So right, the minutes and seconds with degrees and anyways. The meter we actually define by time. We used to define it by wavelengths of light, but now we define it by time. So length and time are more or less, we define them together. Mass, kilogram, we may change the definition of kilogram. Kilogram right now is a hunk of platinum that we keep. And we have a couple different kilograms, and they're not the same mass. And they're getting lighter, they're evaporating. So we're talking about changing the kilogram and the mole to fit silicon. So silicon has the same isotope. We'll talk about isotopes later. And we'll think about having spheres of silicon be the kilograms and the moles. Right now, the mole is based off of carbon-12. But if we change it to silicon, then we can change the kilogram as well. Kilogram used to be defined by water. So a cubic deciliter, so you have a meter, a cubic deciliter is a liter, and 1 liter of water was a kilogram. Or 1 cc, 1 cubic centimeter of water, a milliliter of water was a gram. It still is a gram. That used to be the definition. Now we use platinum. So, but this may change. But we'll see. As of right now, it's a hunk of platinum that sits in a vault somewhere. Then we can take these, not candelas, but the rest of these, we can then derive other units. So this is more physics. Don't worry, this is not a physics class, it's a chemistry class. Couple things like a Newton. This is ugly looking. So, so force is mass times acceleration. So mass is a kilogram, acceleration is meters per second squared. So this is a force of a Newton. And then Newton meter is a kilogram meter squared per second squared. This is a joule. And a watt is a joule per second. A watt is then mass length squared over time cubed. So some of these terms that you see, they're just units that are derived by other things. And we can also take a base unit and then multiply it by a certain amount. So if you look at meters, we can multiply it by 1,000 and have a kilometer, kilometer. We can multiply it by 1,000th and have a millimeter. So having the base unit of meter, I can describe something as small as an atom. An atom's going to be somewhere between 50 and 100 picometers. That's 10 to the minus 15. So pico is 10 to the minus 15. So an atom, you can use it to describe people. People are usually around 1 to 2 meters in length, right? Then you can describe it something like the Earth. And the Earth, the diameter of Earth is 8,000 miles, so that would be whatever that times 1.6 is. That would be 12,800. So 13,000-ish kilometers is the diameter of the Earth. So, of course, the Earth is oblate, so it would be an average. So using the same unit, we can describe anything. We just put a factor in front of it. And that prefix is a factor of 10. And we can also derive other units just from the same unit. So I already mentioned a liter. A liter is a cubic decimeter. So deci means 1/10. So if you take 1/10 of a meter and you you make a cube of it, that's a liter. So if you wonder where the liter comes from. And cc's, cubic centimeters, the same thing as a milliliter, kind of thing, a thousandth of a liter. Okay. Are there questions so far? Okay, now we can finally get into some calculations. So density, here's another thing. Density, mass divided by volume. Density is also known as an intensive property. So the intensive property is independent of the amount of something. So what is the density of the water in this water bottle versus the density of the water in Lake Tahoe, if you've ever been to Lake Tahoe? Is it the same or is it different? It's the same, right? So density is intensive. It doesn't matter how much stuff you have. What is the volume of the water in this water bottle versus the volume of the water in Lake Tahoe? Yeah, it's different. Yes, less different. So that is an extensive property dependent on the amount of something. So mass. Mass is another thing. So the mass of the water here versus the mass of Lake Tahoe. I wish I could lift up the mass of Lake Tahoe with this one arm so easily. So that is dependent on the amount. Okay. So here's an example. This is an easy one. A man receives a platinum ring from his fiancée. Before the wedding, he notices the ring feels a little light for its size. Decides to determine its density. He places the ring on a balance and finds out that it has a mass of 3.15 grams. Then the ring displaces 0.233 cubic centimeters of water. Is this ring made of platinum? So the placement of water, that's, you can, if you put something in water and you see how much the water rises, that tells you the difference, how much it rises, tells you the volume of what you put in. So the mass is 3.15 grams, volume is 0.233 cubic centimeters. What's the density? Then it's just the density is just mass, 3.15 grams, all over 0.233 centimeters cubed. They've already calculated this out. That is 13.5 grams per cubic centimeter. And the density, that's too low. The platinum density is 21.4 grams per cubic centimeter. So because of that, this is not this ring is definitely not made of platinum. So the person that originally figured this out was Archimedes. So there's a story about him. I think he was Greek. I'm not sure, but the king was worried. He sent some gold to a goldsmith to make a crown. The king was worried, like, did the goldsmith steal some of the gold? Because you can mix 14 karat gold looks like 24 karat gold. I mean, they look pretty much the same. 10 karat gold, same thing. He was worried, like, oh, did my goldsmith steal some gold? So he asked Archimedes to figure this out, and allegedly Archimedes was in his bath. He's like, I need to think about this. And he go in the bath, and he saw the water level go up. He's like, oh, I know what I can do. I can figure out the density. And then he was so excited, he ran to find the king naked and tell the king. So that's the story. I don't think this is going to be verified because it's a legend. Okay. All right. Changing topics yet again. Significant figures. So when we report data, we have a way of saying how well we know something. And how well we know something is the significant figures. So distance, usually when I measure distances, I sometimes use my step tracker on my cell phone. I can also use my car's odometer, right? So if I want to know how far is it between my house and Maui College, I can just like look at my odometer and say, oh, it's 3.6 miles away. I don't know. I'm just making these numbers up. So, but uh, when we first went to the moon, one of the things we did is we placed mirrors on the moon. And about 4 times a day, we check the distance between the Earth and the moon. We shine a laser light on it, and we can then, from the time delay, we can see how far the moon is from the Earth. And what we found out is that the moon is moving very slowly away from the Earth on the order of about an inch per year. And we believe that the moon was much closer to the Earth when it was formed. We think that the moon was formed by something called the Great Impact. There was a Mercury-sized planet that collided with the Earth, and then that created a ring around the Earth, and that congealed to form the moon. And because of the water on the surface and the drag, the moon is moving slowly away from the Earth, very slowly. Eventually, we will become completely tidally locked, and the Earth and the moon will rotate with each other. But the moon is tidally locked to the Earth. Mercury is tidally locked to the sun, meaning that we have the same face. The moon is always, the same face is always facing the Earth. But that to have that laser get the distance, it's very, very precise. It has a lot of significant figures. My car's odometer is not even close to that, right? I couldn't tell an inch over a year with my car's odometer. So there are measurements that are much, much more exact. And we can dictate that by the number of significant figures. So if you look at this, so if you look at this number here, 5.213, say I say something, this is 5.213 seconds. I'm fairly certain about the first three figures, the first three. The last one, though, I'm kind of guessing. And to show you this, let's look at this measurement. Say I want to measure what is the volume of this. So I would look at this and I see, okay, there's 4 milliliters, and this is 0.5. So the meniscus right here, it's somewhere between 4.5 and 4.6, and I'm going to guess, 4.5. It's either 7 or 8. I'll go with 8. I'm feeling positive today. What is that? This is 4.57. Shoot. But the point is that this is about plus or minus maybe 0.01 in that range, and so 9 of the book said 4.57. So we can look at this and we can kind of guesstimate the last number, and so this may seem kind of strange for us right now. My advisor, my PhD advisor, he's I don't know exact age. He's in the order of 80 years old. He remembers when computers came into science, and people used to be they would take a lot of pride on how well they could read things. Like, I can read that down to 3 significant figures, and I feel really good about that. And then computers came along, and then they would just, blow everybody away on their reproducibility. In a way, taking measurements, like humans taking measurements, has already mostly been replaced by computers. We're getting a lot of things being replaced by computers. This is one of them. No one even thought about this. You're like, when am I actually going to read something? I guess in Chem Lab, that's one of the few places you're going to have to read real data. Most of the time, we have an instrument do it for us. I don't need to calculate my speed. I have a speedometer. Why do I have to calculate my speed? I have a computer do that for me. Police officer, same thing. I just use my radar gun. And it tells me. I don't have to do any math. So we will do this in lab, but it's, in a way, it's kind of, we humans are not doing this as much. But if we're not using it as much, why are we doing it? There are some cases where we still have to do it, and this is also for learning. So meaning, what is the purpose of the university? Why do we have a university? A university is here to generate new knowledge and to preserve old knowledge. So having chem lab where we actually pour things in, we are preserving the old knowledge, but we're also using it to train you guys. So it has a couple purposes. So we are generating new knowledge. Not as much as, say, like UH Manoa, right? They're a research institution. So they generate lots of knowledge. We do generate a little bit, but not a whole bunch, not like other schools. But okay. But hopefully, as you're doing this in lab and in a few examples, you can see the importance of sig fig. Well, the importance of sig figs is because you need to know how well you know something. And some things you need to know very well. So if I'm making a cocktail at home, I don't really need to have very precise measurements on something. If I'm making a intravenous solution that I'm going to inject into somebody, that's something that needs a little bit more control, right? So, and we know this. We know, and then so how can we tell? Oh, this is a very well-known substance. We do it by sig figs. So here are some of the rules. So sig fig rules, significant figure rules. All non-zero digits are significant. So, and interior zeros are significant. Leading zeros are not significant. Trailing zeros are categorized as follows. After decimal point, they're significant. And so this bullet point number 2. Trailing zeros before decimal point are always significant. Trailing zeros before an implied decimal point are ambiguous and should be avoided. And also just big numbers like 4 billion. How many? If you say that, then you would think that that's ambiguous. The number of ambiguous means you don't know. You don't know how many sig figs that has. So sometimes they put if they give a number like 4 billion, if they want to show that it is in fact 4 billion, they'll put a decimal point at the end. And these are commas. That point then indicates that the number is significant figures. And then exact numbers, they have an infinite number of significant figures. I have 10 fingers. That's not 2 sig figs. So saying 10 figures, it's a 1. 10 fingers, that's an exact number. That has an infinite number of sig figs. It doesn't mean I have 1.0 times 10 to the 1 fingers. So I'm not sure about how many fingers I have. No, I know I exactly have 10. Okay. So I know we got 3 minutes of class time left. You know what? I think this is a better thing to come and talk about on Wednesday. We don't have that much left in this chapter, and we'll be over it, completed very soon thereafter. But we'll pick up here where we talk about. Does anybody have any questions? Quick questions. I know that we'll cover it again a week from now. It seems like so long. Okay. Sorry for the long talks today.
Has the Pearson issue been resolved?
Yeah, Pearson.
I can't read it.
Okay, let's.
Can you help me?
Yeah.